A supernova, the most devastating event in the universe, the actual death of a star. And from that death, new life. Rare in human terms, but common in the life of the universe, these colossal explosions are responsible for all but a handful of the known elements. One or several explosions like it were responsible for the ejected dust and gas which began to spiral together some 4.5 billion years ago. As this gas and dust spun, gravity caused it to coalesce, to form larger and ever larger bodies of matter. The great majority of matter collected at the center and formed a new sun. The smaller masses formed the 9 satellites which circled it. All matter within these satellites, every molecule in fact, has made this transformation from space dust to sun and planet billions of times. Due to circumstance, only one of these satellites that we know of ever developed the environment which would support the most fragile of all matter, life. Life on planet Earth was born of the sea. The huge bodies of water which covered 2/3 of its surface gave birth to billions of different forms of life. Upon its advent, the life forms were nothing more than single-celled organisms, like blue-green algae, creatures who thrived in an atmosphere of nitrogen and carbon dioxide. As evolution progressed, some of these individual organisms learned to cooperate to form colonies. The cooperation of these colonies proved successful, immensely successful. The organisms which began to work in groups flourished and covered all of the many shallow areas of the seas. Some of these organisms were the algae called stromatolites. The vigorous abundance of the early algae, trillions upon trillions of individual organisms, actually created something of a prehistoric pollution problem. A poisonous waste gas they produced began to accumulate in the atmosphere to levels which were lethal to many creatures then living. This poisonous gas was oxygen. It was a gas all species had to adapt to or die. Most of those later species who did make the change learned to live with oxygen so well that eventually they could not do without it. The stromatolites, in addition to releasing oxygen to the air, removed carbon dioxide from it. This latter gas they trapped in tissue as other algae did, but also in another solid material, calcium carbonate. They secreted calcium carbonate to help give them better protection and stronger bodies. The emergence of life changed the Earth. Individual lives were small, but their total effect was massive. These small creatures made all life on Earth possible. They altered the atmosphere by releasing oxygen and capturing carbon dioxide. The carbon in their secretions became over the eons a mineral which man has used to shape and form his world. That mineral is known to us as limestone.
Limestone is basically formed in the marine or the ocean environment. It most commonly starts with biological life, shelled creatures, live and die. Their shells are left settled to the bottom. Over the years, this material is actually buried deeper in the earth. It's subjected to pressure. It's subjected to heat. These materials recrystallize and kind of grow together, form nice crystalline patterns, and in the process form the rock we call limestone.
Limestone is sedimentary rock formed from shells and other limy material in the oceans that encompass the world. Outstanding regions of this sort in the United States are the present site of the Rocky Mountains, the Appalachian Mountains, valleys of the Mississippi, Ohio, and St. Lawrence rivers, and a large part of Texas. It is not known precisely when man first started using limestone, but we do know that it was used extensively by the Romans, who incorporated limestone into their vast aqueduct system. At some point in unrecorded time, humans learned that limestone could be transformed into another material that could be utilized in countless other ways. It seems that early in man's history, some observant individuals must have noticed how a bonfire changed the quality of certain rocks and gave them properties they found useful. Today, this material is commonly known as lime. Mankind has been doing this burning of the stones for a very long time. As it takes a lot of heat to burn stone, men learned to get the most from the fire they used. From the bonfire, which was not efficient, the vertical kiln was developed. The developments in the processing of limestone into lime, known as calcination, have followed the developments of other technologies, as man discovered more and more uses for this natural material. As the ages progressed, so did the technology of lime production. There are numerous steps in converting limestone to lime, and each has been carefully designed to be as efficient and clean as possible. Today, limestone is mined widely throughout the United States. It is not surprising the locations of high-quality limestone formations match the areas where the seas once covered North America. Often, the sites mined are, in fact, ancient fossilized reefs. Though the technology for producing lime from limestone may have become more efficient, it is important to remember that the process has remained essentially unchanged from the time of the Egyptians and Romans. Limestone is a natural material and is non-hazardous and non-toxic. Other forms of calcium carbonate, in fact, are clam and oyster shells, which are also used in the process of producing lime. Limestone deposits still bear evidence of their origins in the form of fossilized clam and seashells. Modern-day limestone operations are designed and built to be environmentally sound and clean. Today, limestone operations utilize the latest technology to extract the mineral from the earth. Once a site is prepared, the stone is released from the ground by the use of explosives. The blasting is done in a way that fragments the rock into manageable chunks. The newest mining methods are designed to minimize any dust resulting from the blast, as well as noise. Heavy equipment is then used to move the broken limestone to the rock crushers. The rock crushers are used to reduce the broken limestone into sizes suitable for further processing. To get the best use from the mineral, it must be roasted, or more properly, the term is calcined, at over 2,000 degrees Fahrenheit in kilns. At these temperatures, limestone is converted to lime. This transformation produces the lime that is used in literally thousands of applications in daily life. After calcining, white lumps are left behind. This white material is nearly pure calcium oxide. It is calcium oxide, lime, that is the most useful of chemicals. The lime produced in the United States is of a superior quality with high chemical purity. It is called quicklime at this point because of the way it reacts with water. Water can be made to boil simply by adding lime to it. The resulting chemical is then transported by dust-controlled conveyors to storage silos and then delivered to various locations around the world for use. In every phase of the operation, dust is controlled because a clean, efficient operation maximizes the output of lime and yields a high-quality product ready for use. An important point to note is that most chemicals today are getting a lot of bad press because of the harmful byproducts released when they are produced or used. Pollutants in the wastewater of industrial plants injure fish as well as the creatures who feed on the fish, sometimes people. We seem to be surrounded by poisons of our own making. As opposed to this, lime, also a chemical, is exceptionally beneficial. When people look at the diverse ways this compound is used, there is a growing appreciation of lime's contribution to a clean environment. Some 4 million tons of lime a year go directly toward uses that protect and preserve the environment. Lime is the most versatile chemical utilized to help safeguard the quality of our natural environment. As an example of the broad range uses of lime, consider this. Pollutants enter the environment as wastewater discharged into streams and rivers, dispersed in gases released into the air, and discarded as solid wastes that contaminate soils and groundwater. Lime can be used to clean up and remove these harmful pollutants before they are released to the environment.
Well, both on the laboratory scale and in the field scale, we're investigating technologies by which calcium-based sorbents, lime hydrates, calcium carbonates can remove a number of different compounds that we commonly refer to as air toxics. And those include compounds like mercury, cadmium, and different compounds associated with mercury, mercurous chloride, those kind of things, dioxins, chlorinated dioxins. So we're working on developing a lot of different technologies that use lime-based sorbents for chemically tying up these materials and preventing them from becoming emission problems. Well, what we're trying to do is develop efficient and economic ways of removing pollutants from the gaseous emissions from a number of different industrial and utility sources. And if we can capture these pollutants and dispose of them in a more environmentally acceptable manner, that's a lot better than dispersing them all throughout the atmosphere.
With regard to water, more tons of lime are used to purify our drinking water than any other chemical. Lime is used to soften water, to remove particles by coagulation, to neutralize acidity, and most importantly, to eliminate heavy metals such as lead.
Lime is a natural product. Lime is the skeletons of organisms that were deposited millions of years ago. We've mined that material, we've processed that material, and we use it back to treat products that we put back into the environment for human consumption, like water.
As our drinking water can be purified with lime, so too can our wastewater be treated to make it safe for discharge back into the environment. Here again, it neutralizes and removes unwanted pollutants, allowing purified water to flow back into streams and waterways. The resultant sludge can then be dewatered, treated with lime, and transformed into a material which can be used as a soil-enhancing fertilizer.
In that process, we produce a material that has achieved a PFRP, and that product is still relatively high in nutrients, and because we've added the lime, the pH is very high. We can use that not only as a nutrient source, but as a source of agricultural lime for farming operations here in this area or anywhere that needs lime in their soils.
This sludge to fertilizer process is being used in many parts of the country. Its benefits are multiple. Not only is the waste cleansed of pollutants, but the resulting mixture of lime and sludge is transformed into a usable, marketable product, thus sparing municipalities from using landfills as a means of disposal. One area of pollution on our planet can be quickly rectified with the use of lime. That pollution is called acid rain.
Acid rain results from two major pollutants. One is called sulfur oxide, and the other is called nitrogen oxide. One of the main sources that these pollutants come from is the combustion of coal, and as these pollutants go into the atmosphere, they react with water in the atmosphere and ultimately form acid products. And when it rains, those products come back down to Earth in the form of acid precipitation. And the effect of this acid precipitation is to cause lakes to become acid. There's some indication that it may cause trees to suffer damage. And of course, we see evidence that buildings and structures and monuments and automobile finishes and those sorts of things deteriorate as a result of acid rain.
During the course of the 20th century, the acidity of the air and acid rain have come to be recognized as a threat to the stability and quality of the Earth's environment. Most of this acidity is produced in the industrialized nations of the Northern Hemisphere. The threat posed by acid rain is not limited by geographic boundaries, for prevailing winds carry the pollutants from region to region. Nor are the destructive effects of acid rain limited to the natural environment. Structures made of stone, metal, and concrete have also been damaged or destroyed. Some of the world's great monuments, including the cathedrals of Europe and the Colosseum in Rome, have shown signs of deterioration caused by acid rain and the burning of fossil fuels. In order to combat acid rain, lime is being utilized in several different ways. Lime is finding great use in the neutralization of acid-producing gases in the smokestacks of power plants, cogeneration plants, and many industrial facilities. The idea is to stop acid rain at its source.
Lime in some form or other, whether it's in a scrubber, or whether it's dry injection in the furnace, or whether it's duct injection after the furnace, it's going to take some lime product to accomplish that.
One of the problems often encountered in attempting to clean up the environment is that the cleanup operation often creates another form of the same problem. For example, a company has a solid waste pollutant. They burn it, and the result is a gas pollutant. They install smokestack scrubbers to capture the gas, and the water used in the scrubbers turns into a liquid pollutant. When they dewater the liquid, once again, they have a solid pollutant. We could call this the pollution cycle. Lime can be used to break this chain at any point. Pellets such as these are one of the ways to do so. They are made by mixing lime with ordinary household refuse. In this case, a waste material is converted into a commercial product that is an excellent source of fuel. These fuel pellets burn almost as hot as coal. What is better, the lime in the pellets neutralizes the acid gases produced as coal and refuse are burned. The benefits are multiple. Harmful pollution gases are not released to the atmosphere. A low-cost fuel supplement is utilized, and the sale of the pellets helps to pay for the refuse-to-fuel conversion process, and demand is reduced on our landfills. In some instances, these pellets may allow older plants to operate cleanly without having to install additional pollution control equipment. Another such cycle is related to the disposal of household trash. Americans generate over 165 million tons of trash every year. With landfill space at a minimum, or even non-existent at most major population centers, municipalities are faced with exorbitant costs to truck garbage to distant, out-of-state landfills. An efficient method to reduce the volume of this trash is to burn it as fuel to produce steam or electricity. The electricity can then be sold to the local utility. These trash burners, or municipal solid waste cogeneration plants, produce acidic stack gases, which are cleaned using efficient lime scrubbers.
Some other principal concerns of municipal incinerators that are not present with power plants are the formation of dioxins in the furnace and the amount of mercury that comes in through, because it is handling industrial and municipal waste. The mercury emissions are substantially higher. Lime appears to enhance the controllability of these. One of our researchers is injecting lime directly into the furnace to prevent dioxins from being formed. We're also looking at the role that lime plays with the dust collector, because it appears that lime will enhance the capture of mercury as a solid material in the dust collectors that are used downstream of these scrubbers.
What we're doing is, in the laboratory on a small bench scale, is we're trying to understand how the presence of lime affects chlorinated dioxins, which is an extremely toxicant matter that we're trying to get rid of. And what we found so far is that we believe that there's some sort of a chemical reaction that occurs between the lime and the chlorinated dioxin. And it's good news because we are hopefully rendering the dioxin non-toxic.
Another exciting prospect for the use of lime is in the treatment of hazardous wastes and remediation of contaminated Superfund sites. Many of these wastes are extremely toxic and can cause cancer and genetic defects.
Quicklime by itself is not believed to be the cure for PCB contamination. However, by using the DCR process, which takes advantage of the fact that the quicklime is hydrophobized to make it preferentially react with organic materials rather than aqueous materials, it allows us to adsorb the PCB in a PCB contaminated soil matrix and free up the PCB such that it's more subject to attack by other reagents that might be introduced. And we've been able to demonstrate with the DCR technology that with the addition of additional reagents, in addition to the hydrophobized calcium oxide, we're able to dechlorinate, that is, remove the chlorine from each of the PCB molecules at ambient temperatures in the solid phase in the soil in as little as 24 hours.
Currently, lime is being used to restore the ground where waste oil ponds once stood. Quicklime is used to dewater the sludge and stabilize and solidify the oily waste so the ground can be compacted and converted to useful purposes.
The DCR technology has widespread application in dealing with oil sludges and in dealing with waste oil lagoons. Normally, a lagoon that has water and oil mixed into it has a very large volume of material that needs to be dealt with. And a lot of technologies require that you first separate the water from the material. So you have two phases that you have to deal with. The DCR technology can deal with water and oil in basically infinite varieties of mixtures of oil to water ratios. And all you have to do is vary the amount of the hydrophobized calcium oxide, the starting material, at the beginning of the reaction to the particular case in hand. So one reagent is capable of dealing with a wide variety of water to oil ratios and sludges.
More recently, another use of lime has been developed which can help solve the worldwide problem of crude oil spills on land and in the ocean.
Other applications with regard to oil spills include the actual application of the hydrophobized lime to the contaminated beach substrate. This has been proposed, and it would very effectively tie up the oil. If you have an oil-contaminated shoreline, you could apply the material right there on the shoreline, mix the oil with the hydrophobized calcium oxide, allow it to hydrate to form the hydroxide, and then allow it to react with carbon dioxide either in seawater or from rainwater or just in the air to form calcium carbonate.
In the whole universe, Earth is the only place we know of where there is life. All living things have, to one degree or another, shaped the Earth, but none so fast as man. Intelligence and technology magnify our capacity to change the planet we live on. With the discovery of fossil fuels, men drew upon the energy which took early plants eons to lay down. In utilizing lime, we again tap into that same ancient source, but for a different purpose.
It's amazing, yes. The number of things, the different industrial applications, the different environmental applications, the myriad of environmental applications of this product is wonderful.
Though chemicals are not intrinsically either good or bad, it seems appropriate that lime from the limestone acts as a counterweight to the effect of man-made pollutants upon the Earth. It is important for us to remember that the Earth is a closed system. All of the elements that have been present or ever will be are here now. We have learned all too well how to exploit nature to provide us with energy and technological advancement. We must now look to the Earth once again to heal the wounds which we have wrought. It is only appropriate that we look back to those tiny organisms whose lives made all of ours possible. We now call upon them again to give new life to areas of the world brought to the brink of disaster by man's casual misuse of the riches of the planet. It is up to man and his use of our natural resources to ensure that it remains so.